saw how to create a vector and a matrix, and in this particular video we're going to start off by looking at how we can print values to a command line and effectively to a file as well. So for that we have to first create an array. So suppose we want to print the vector. So suppose we want to print the vector like this. I mean, of course you can simply loop over the elements of AB, but that is not useful in this particular context, because once you start programmatically declaring your arrays, you won't be able to have such an easy access. So what you will have is the vec object B, and eventually you want to print the elements of B, right? So let us create an array. So double star ABB. So I'm using ABB because AB is already used. So essentially this holds, or rather this will hold the value of B. Alright, so we've declared double ABB. So before destroying we have to write certain lines. So we will do vec get array. So vec get array is a function. So let me just take you to the function reference. So vec get array returns an array which contains the processor's portion of the vector data. Okay, so vec get array requires the vector object X and the petsy double star A. So because we have declared it as this, we have to pass the address of ABB rather than simply passing ABB. So we must pass B and the address of ABB. So another useful thing is you must call vec restore array when you no longer need access to the array. So Petsy tries to keep everything in its own data structure. By calling this, you're actually transferring the vec object to a simple C array ABB. So we must also follow up by the vec restore array. It has the same syntax. So let us do that. So it's simply restore. Okay, so this will now help us to print the values of ABB. So what we will do is for I equal to 0, I less than 4, I plus plus, printf percentage %lf slash n, and we will print ABB I. In fact, let us print I as well. So let's just put a percentage %d next slash t. Alright, so let us compile this. So the make file will be, the make target will be make declare vector, alright, dot slash declare vector. Okay, so we could finally print this, and at the end of restore it deallocates ABB. So once this line is executed, we cannot do this anymore. So now you can imagine, instead of having a printf, you could alternately do an fprintf with this an fid, and then you simply f close fid. So for that we have to declare file star fid, then so it's a pointer to a file, then fid equal to fopen data file dot dat write, and yeah, that's pretty much it. So this should allow us to write the data to a file and then close the file as well. Let us see what happens. So let us go to the folder and see whether we have something data file.dat. Let me, why is it not opening? Great. So we do have the data inside a data file. So it's quite useful when you want to, so suppose you want to post process data. Once you have this, you can then plot it using Python or GNU plot, anything you like. It's always useful to have the data file when you're working with it. So this is a small snippet and I'm not gonna discuss more about this. We'll use it when we will need to. Okay, so it's quite useful, a versatile bit of snippet which you will find useful time to time. So similarly, similar to get array, there is also mat get array. So it does the same thing, right? Instead, it has to be passed with mat and petsy scalar the pointer to v, okay, the location of the values. So yeah, we'll and it has to be also called with a mat restore array. So we'll do it whenever we'll require it. Okay, so don't worry about that. Okay, so let's move on to solving this particular set of equations. So what do we have? We want to solve this, and yeah, so let's see how we can solve. So it's not a very formidable set of algebraic equations. It's rather easy to solve it by hand as well, but it's a bit time consuming unless you're a mathematical savant. But anyway, so we will use, so let's copy this code. Let's not, so let me save it. We'll write it as solve simple, solve sim. I forgot to put the extension. Let me just go to the folder and rename it .c. All right. Yes. Sorry. All right. So let's remove this ABB business. We don't need it for now. Let's remove the file ID. Let's remove this bit of program. We don't need it. I mean, if at all you need it, you can always rewrite that bit of code. So now we want to have another vector x which will store the solution. All right, and we built the array, we built the vector. So now we need to have an object which will help us actually solve the thing. So in PETC, the solvers are a part of the object Ksp. Okay, so we will declare it as Ksp. This is the data type, and we'll call it small ksp. So Ksp is the solver object. The solver object will operate on the vector, the matrix A and the vector B to yield a solution X. That is how it works. So similar to the matrix or the vector creation, so this is the vector creation, this is the matrix creation, there has to be also a solver creation. So the steps are quite similar. So it contains ksp create, and finally, so there is no ksp assembly, but ultimately you have to destroy. So there will be a ksp destroy, and we'll pass the address of ksp. Okay, and eventually we have to also destroy x. So these are some things you need to always do. So once we create ksp, again it has to be done on com world, and we have to pass the address of ksp. That's common. Then ksp set operators, so it will have the ksp object and a comma a. So ksp set operators actually sets the preconditioners. Let me just show you. So it contains the matrix which defines the linear system and the matrix to be used in the preconditioner. Usually it is the same as a, right? That is why we have passed a comma a. If it is something else, you are always free to give this a different name. But in this case, we are gonna pass the same matrix to create the default preconditioner. So we've set the operators. Then we will do ksp set from options, and this will simply act on ksp. And set from options is usually going to use the flags that you supply from the command line. So various kinds of preconditioners, solvers, whichever you want to choose, you can always pass it from the command line to the code, and during this particular step set from options, it will set the particular options that you set. So ksp set from options. So the point is, the help files, you can have an offline version of it, but I'm keeping it I'm accessing the online version of the documentation. So the function reference from ksp set from options is simply passing ksp. The database options are maximum iterations, relative tolerance, absolute tolerance. Okay, so the guest type, the monitor, things like that. All right. So this is something you need to always do. Then what we will do is, so before all this, we need to sort of initialize what x is. So what we will do is simply take whatever b we have and initialize x with the value of b. So we will do vec duplicate, and we will duplicate b into x. So we have to pass the address of x, right? So after setting from options, we'll simply do ksp solve ksp b comma x. So ksp already has the information about the matrix a. We have to pass the right hand side and the solution vector. So before anything, let us quickly see whether we have a good compilation. Excellent. So no errors. Fine. Oops, actually this is a new file, so we need to modify our make file. So let us create a target for this particular soul sim system. So we have to make a new target. Replace. That's it. So we need to now compile this particular target, not the previous target. Alright, so we will do make soul sim system dot slash soul sim system. You have to allow this. Don't have to do anything if you're using GNU Linux by default. Well, everything runs fine. So now we can finally output the vector x. So we can copy this vec view, and before destroying, we can simply visualize x. So x has to be an array of size 4. So let me recompile. So this is the solution that we obtained. Alright, so x1 is 2.051, x2 is 0.596, x3 is 2.117, x4 is minus 1.760. Yeah, I'm just taking 3 decimals. Let us quickly see whether it checks out. I'm shamelessly opening a calculator, but anyway, let's check for the first equation. 2.051 plus 4 times x3, which is 2.117, minus 2 times 1.76, 6.999, and it's as good as 7. So I'm truncating it at 3 decimal places, but you get the point. So far, we've made a Ksp object. So Ksp stands for Krylov subspace. So if you go into the area of solving large matrices, you necessarily have to go into the theories of various kinds of solvers, and invariably you'll end up with solving with the help of a Krylov subspace. So Krylov subspace contains a lot of methods inside, but they are all part of what they call as Krylov subspace. So we're not going to discuss the theory of all those. They are left for you for a more specialized course on linear algebra perhaps. But yeah, once you start doing the course on linear algebra, what you can do is make a detour of all those problems that you do. You can try to numerically experiment with the help of PETC. PETC allows you that massively scalable set of functions, data structures, libraries, if you will, and you can do a lot of things, you can experiment a lot of things. Yeah, so this completes the creation of vector, the matrix, the display or the printing of a vector to a file, and solving a system using a Ksp object. So in the next example, what we're gonna do, in fact, before going to that, what we can do, so what we had was, we had seen vec view, something like this. So it showed the different vectors that we had, and there was also a mat view, something like this. But there is also a Ksp view that shows us the information about the method used. So what do we have? Unable to scroll up. Okay, what we can do is pipe it to a file. We can look at the log file. So Ksp Object 1 MPI, it's using a GMRES. So GMRES stands for Generalized Minimum, well, I forget the full form. GMRES, Generalized Minimum Residual Method. Okay. So that particular method has a certain number of restarts. It has a breakdown tolerance, maximum number of iterations, preconditioned norm for convergence test. It's using a preconditioned, it's using ILU, incomplete LU decomposition, as the preconditioning, and it shows all the information that you need. Okay, so what we can do, in fact, is change the solver type at runtime. So what we can change various options. In fact, we can change various options. We can do minus Ksp type GMRES minus PC type B Jacobi, block Jacobi. Let's see. It obviously gives the same answer, but it uses a different preconditioner. We can also do a minus Ksp monitor to see how the progress is. So immediately after one iteration we have convergence, which is expected for such a small system. Okay, we can use a preconditioner which is not the ILU but in fact a simple LU decomposition. So we can change various options at runtime. Okay, so what are the different options available to us? Let us see minus help. So it shows all the different. Okay, I cannot scroll. Minus help. In fact, let us get only. So it has various kinds of. So let us pipe it to a file. Let us pipe it to a file so that we can open it easily. So help.out. So what does help.out contain? It contains the help string that we put. Then it contains a bunch of options that you can pass. So what are the different, so it shows you the different vec view options. It shows the different matrix options. It shows the different viewer options, the different preconditioner options. So ILU, then you have Jacobi, PB Jacobi, VPJ Jacobi, B Jacobi, SOR, Shell, MG, Eisenstat, ILU, ICC, Koleski, ASM gas. So different kinds of preconditioners are present. So we are more interested in the Ksp options. So there are a bunch of options and we want to extract this line. So how do you extract this line? So there are in Linux there are specialized tools. One of the specialized tools is called as grep. So it will scan. So we're piping this help output to grep, which will give us the line which contains the keyword. So the keyword will be, the keyword we want is Ksp type. So we want to give it Ksp type. So the output of grep is shown over here. So grep is a Linux tool, you don't need to worry about it. So one of these methods, cg, grep pcg, pipe cg, pipes cgrr, a host of methods, minres, fgmres, biconjugate gradients, stuff like that. So you have a whole set of methods that very efficient and intelligent people have coded so that you don't have to go ahead and code all this. But remember, it always helps to know what each algorithm does inside out. But it's unlikely that someone like me is gonna write a code which is multiprocessor, which is more efficient than what these people have written. It's unlikely. So, in fact, let's change some more options. So now that we know these methods exist, we can call minres. So it uses the minres thing. It gives us a slightly different norm after one iteration, but it has already converged. You don't need to worry about it. So yeah, that's how you can choose solvers at runtime. I've shown you a few Linux tips and tricks. So now let us solve a tridiagonal system. So what I'm trying to get at is, if you're solving a boundary value problem in 1D, say d2 u dx2 equal to sine x, right? If you're trying to solve this, so what will you do? You're gonna split this into a discrete form over one central node, one right node, and one left node. So what do you have? You have ui plus 1 minus 2 ui plus ui minus 1 upon delta x square is equal to sine xi. And then, as we've seen in the Python code, you assemble this matrix. When assembling this matrix, apart from the boundaries, you get a tridiagonal system. Okay, so the diagonal elements will be -2, the off diagonal will be 1, the left diagonal will be 1. It will keep doing this except the boundary, because at the boundary the value of u will be specified, or the gradient will be specified, after which you can take a ghost node and you can find out the appropriate boundary condition using this equation itself. And we've covered this, how a tridiagonal system comes into existence. So this kind of tridiagonal system has to be oftentimes algorithmically done. I mean, in this particular example it's still very easy, but nevertheless you have to build it for an arbitrary size. We don't restrict it to a 4x4 matrix, so we must write the code so that you can assemble the matrix for any arbitrary size. So let's see how that can be done. So yeah, so first of all we're gonna have hash include std and not std, have petc.h int main int argc char star arg v. So let's save it as tridiag.c and we will return petc finalize. Alright, so we're gonna define the vectors as we did in the last code, x and b. We're gonna define the matrix A. We're gonna define the Ksp object Ksp, and what we're gonna do now is define the integer m. What will m do? It will hold the size of the matrix, and we can put some default or we can overload it with the help of some command line argument. Let's keep it m for now. And yeah, let's write m equal to a to I of argv first thing. So we must pass through the command line argument the integer that is the size of the matrix. So let us include stdlib as well, just in case. Let me put this before this. Okay, so m contains this, and we'll define all the other parameters as we go in the code. So first things first, we must do a petc initialize. This should contain petc com world, and no, this should not contain petc com world, rather it should contain the address of argc, address of argv, and null, and some help string. Alright, so now we have to do the same set of lines, and which we had done, well, we had not done, but yeah, we need to declare the vector. So let me copy this. Let's not waste time in writing all this. We have to create the vector. So this bit of code is to create the vectors. It's good to always type down some comments, meaningful comments. So what kind of vector do we want to build? So we want to build, let's create x, and the size will be m. It will not be 4. Alright, it will be m. So we'll build, so set values we have to get rid of because we're gonna do it somewhere else. Alright, let me keep it. We don't need, and we can delete it for now. So we just do set values of options. Once X is created, we can also create B. So we can do vec duplicate. So we're gonna pass X and the value of B. So essentially we have created a duplicate vector B. Alright, then in fact we're gonna make a very synthetic problem. So we will need something called as X exact. So what we're gonna do is quite simple. We're gonna take our differentiation matrix A. So we're gonna create this A to be created. We're gonna create X exact. That is, we'll populate this with something which is known. Okay, and then we're gonna multiply these two and find out some matrix B. Once we have B, then we're gonna synthetically solve again. So A is known, X will now be unknown, equal to B. So we're gonna solve this afterwards, and we're gonna compare X exact and X. Well, in an ideal world they should be exactly equal, but let's see, because we're using iterative algorithms, we will have large matrices and they may be close but definitely not equal, and that's a thing you have to live with numerical algorithms. So set from options X, we're gonna duplicate, we're gonna make another duplicate of X comma ampersand X exact. Alright, so far we have created the three matrices. Now we're gonna create matrix. So again, we're gonna reuse some of the code. We're gonna reuse this. So we have to create the matrix A. We have to set sizes. Instead of 4, it will be M, right? Then matrix set from options A. Good. What else? And we have to do matrix mat setup A. Is something which we have done over here as well. So once we have this, we have now created the two vectors, rather three vectors, and the matrix. So what we are gonna do is we're gonna first obtain the loop range. So let me show you. We're gonna do mat get ownership range A. This will be start end. This will be end end. This means it will look at, so the program will look at the array A. If you have multiple processes, it will distribute the index over which the program is going to loop. It will divide A into sub chunks. Okay, so it can have something like this. Start end is this, end end is this, start end is this. So it depends if you're doing it in parallel or not. Simply speaking, start end and end end will simply contain the dimension of the array. So hence the ownership range. Different processors will own different ranges. And what we can do already is, so we have to declare start end and end end, because we have not declared them, so they need to be declared as integers. So let's do that. So over here we need to make int start end and end. So we have created the start end and end end. So in fact we can print it out, and I'll show you. Before doing all this, let us print out certain parts and we'll see what we see. So let me destroy the different things. So let me reuse some of the code. to destroy. We will need all of this. So destroy a, b, x. We have to destroy x exact as well. So let me modify the make file to have a new target. Alright, so we have created a new target. So let me test it. Compiles well. /try tag. Segmentation fault because we have not done anything. Most likely it has ran into something empty. Okay, so I don't know where the segmentation fault is, but let me see if I can print the start end or not. No, so the segmentation fault much before this, but that's okay. So, well, you can actually pinpoint where the segmentation fault is. Most likely it is somewhere over here. After setting up, we've not done anything, so you can always do a printf to see. I mean, you can obviously use a debugger, but if you want to do it the old way, then simply do this, place it at various positions and see when it actually prints. It's not this. We have not passed the number of we have not passed the elements, so that's why m remains undefined and hence the segmentation fault. Well, so let me put this. We do have a big set of error. And it appears to be because of the lack of declaration. Can we scroll? Mm, I don't know. Right. So don't worry about these errors. We'll sort it out. We'll get rid of this. So we have to get the membership range, and what we will do is we'll try to fill out the matrix now. So for I equal to start end, I less than end, I plus plus. So we're gonna fill in all the elements, but we need to define the counter I. All right. So over here we will do if I equals 0, then we must do something else. If I equal to m minus 1, that is the end case, we must do something else, we must do something. All right. So what are these somethings? So if I equal to 0, it's like a boundary condition. So we're gonna set two elements. So let us say we set two elements, that is for I equal to 0, which is the first row. We're gonna set this to be 2 and this to be -1. Everything else is 0. So we must first create a vector which will sort of insert things into the matrix A. So this is exactly in line with how we were inserting things. So we must define J as an array of three things. So these three things we will define at runtime, and we must define double v3. So because at best we're gonna insert three elements. So when I is equal to 0, then we must insert 3 and -1. So v0 will be 3, v1 will be -1. Similarly, j0, that is the column index where we're gonna insert something, is gonna be 0, and the column index where we're gonna should be j1, where we're gonna insert -1 has to be 1. Essentially, this location corresponds to j0. This location corresponds to j equal to 1. So now that we have this, we're gonna simply mat set values. Mat set values. It will be a. So we have to insert in a. We're gonna insert one row. We're gonna pass the row number. We're gonna insert two values. We're gonna insert at locations j. We're gonna insert the values of v, and we will insert values. That's it. Then if we have the last element, we can simply reuse this code. So this will be v m minus 1 will be 3 and v m minus 2, or rather let us put it as a Dirichlet condition. So the first one is more akin to a Neumann boundary condition. So simply v m minus 1 will be equal to 1 and j0 will be equal to m minus 1. This is going to be the last value, and we're gonna insert only one value. Else what we're gonna do is we're gonna reuse this. So v0 will be -1, v1 will be 2. Oops, this has to be 2. And v2 will be -1. So j0 will be I minus 1. j1 will be I. j2 will be I plus 1. So we're going to insert three values this time. So far so good. We have not done something very remarkable, but we've just created the matrix A. Alright. So once we've made the matrix A, let us proceed to set the exact solution as well. So how do you do that? Well, because we're doing this in a loop, we can simply set values of the vector as well. So we can say, let us have the solution as something like x or Mm, let's have a periodic solution, like something like sine I. Well, it's periodic. Okay. So let me. So all these exact values will be simply sine of the row number. So xval equal to in fact we can do an exponential of sine I. So we need to define xval. So we need to define double xval. What else? Once we have the xval, we can simply vec set values x exact. We're gonna assign this value to x exact. We're gonna put one value. We have to give the address of I where we want to insert. We have to give the address of what we want to insert. And finally, we're gonna insert values. Okay, so this is how we can put the exact solution as well. So now with this, we can do the matrix assembly. So let us go to this code and let us copy this snippet. So with the help of this, we're gonna begin the matrix assembly and we're gonna finish it. Similarly, we have to do the vector assembly as well for x exact because we have constructed x exact also inside the loop. So this will be x exact, this will be x exact. Alright, so vec assembly is done. Now what we must do is find out what b will be. So as discussed, b will be actually a times x. So how do we do that? So we do a mat mult. This is an inbuilt function, a comma x exact, and it will store the solution in b. So it expects an input of the matrix, the vector, and the output vector. So we are assigning b a times x exact. Great. Now what we're gonna do is we're gonna create the Ksp object. So we're gonna reuse our code. Well, it helps us save some time. So Ksp a comma a, and everything else remains the same. All right. So let us go to the terminal and see whether we have done some errors. Unexpected semicolon. Okay, let's check. We missed a semicolon over here. Okay, let's see. Oh, there is still some error. We missed a semicolon somewhere. Oh, we have not saved the file. Oops. Don't make these mistakes. Well, there appears to be errors and I'm not sure. Invalid pointer. Let's see. There appears to be an error in vec duplicate. Exact. There it is. There's the small error that was causing the segmentation fault. Well, that's the risk you run if you're copying snippets around. And Well, over time you learn to be proficient in tracking down the bugs, but the way I've tracked down this bug is not an efficient way of tracking it, but hey, if it works, it works. It's not stupid. Well, there is some error. Let's see. Hmm, what is the error? Segmentation fault, out of range. Let's see. Hmm, there's a very obvious error. Well, still some error. Let's try to fix it. Well, that was a very stupid mistake. Well, this kind of things do happen. Yeah, so everything's working nice and well. So we've been able to solve till KSP solve so far, and now we would like to view the vectors. So let's do that. So minus vec view. Okay, so instead of doing a minus vec view, let us do vec view inside the code. Before destroying them, we're gonna do a vec view of x exact. Okay, let's see, let's recompile it, and okay. So yeah, they do look close, 1.16169, and well, this is quite expected. And as a matter of fact, what we can do is figure out what the norm will be. So the norm will be the difference between x and x exact. Okay, so in order to find out the norm, we must first have an operation x minus x exact. So we cannot simply do something like what we would do in Python, like error equal to x minus x exact. This is not allowed. So we must do something which is quite something which resembles something which you would do in BLAS. Okay, so you would do what is called as vec ax plus y. So what this function does is it does a times x plus y, where x and y are two vectors and a is a scalar. Okay, so it does a times x plus y. So but here a has to be minus 1, x and y have to be x and x exact respectively. So that essentially mimics what you want to do, and the only caveat is once this operation is done, it will override one of the vectors. So let me just show you the function reference, and it will tell you exactly what it will override. So it would do y equal to ax plus y. Okay, so the first vector gets overwritten. So over here x will get overwritten with the x will be overwritten by x exact minus x. Okay, this thing will cause x to be overwritten by x exact minus x. That's okay. We just want to figure out the norm. Finally, we can do vec norm, that is the norm of the vector x, because that contains the error now, and the norm has to be a L2 norm. So norm 2, and we will store it inside error of norm. So error of norm has to be declared as a double. So let us declare it as a double. Okay, so we've declared it as a norm. So finally, before destroying everything, we can print out printf error equal to percentage lf arrnorm. In fact, we can write down the grid size as well. So grid percentage d and error is this, and we'll print m and error none. So it will help us evaluate how the error reduces as the number of grids increases. So let us recompile. Let us do it with 4 grids. 5 grids. Well, it shows a 0 error. Let us say percentage e. So the percentage e will have a much better output. So there is 10 to the power minus 15, to the power minus 15, to the power minus 16, to the power minus 14. So anyway, so this is how you would go about doing this. So in this example, we ran into some errors, but those were just errors out of sheer haste. But I hope this program gives you a basic structure of how to programmatically create the vectors that you so desire. In fact, let me make the diagonal a bit heavy, so that making the diagonal heavy would render a larger error. Let's see if that happens. No. Well, you can make very large matrices, but anyway, yeah, so you can define the matrix like this. We used a very synthetic example to set up the problem. After setting up the problem, we solved the problem using the Ksp object. We found out the norm, we printed out the error. Okay, so in the next few lectures we will use this kind of program to sort of solve some PDEs. The rest of the code structure will remain more or less the same, and I sincerely request you to have a look at this program, write your own program, so that you don't do any of the hasty errors that we did. But at least, or at least, the structure should be clear. I mean, the syntax and all, they can come and go, but it should be clear in your head what you're trying to do. Because once that is clear, you'll always find out the syntax to do it. So we're doing it in C. Tomorrow, you'll be doing it in Julia. And after tomorrow, you'll be doing it in some new language that will come out, but the logic will always remain the same. So with this, we end this lecture where we've taken a look at solving a tridiagonal system. This is tantamount to a tridiagonal system. Go ahead and try out different kinds of solvers by changing the type. Okay, you can change it to different types and find out the solution. And with this, we end it over here, and I'll see you next time with a new lecture. Until then, have a nice time. Bye.